So, as Jeremy said, that a lot of my work is around security protocols, okay? And I'm not going to talk about security protocols today, because what I want to do is I want to do something which you should never do as a PhD student or even as a researcher, which is show you a little bit of research before it is actually published, while it is still being created a little bit. So this is really a bit of a new topic for me. But then on the other hand, that's maybe quite a good topic for our summer school, because you're starting to see a bit more of the thinking behind creating the research that's going on here. So a bit of a shameless plug as well, since I mentioned security protocols as well. So we are publishing a book on security protocols as well, which should be coming out soon. So I did wrestle. I should be really talking about that. I should be plugging that, but no. The new topic is more exciting. So this is a bit high risk. So the topic here is about conflicts of interest. So what's a conflict of interest? Okay, and this is in the sense of a Chinese wall security policy model. Okay, so what are Chinese walls? Chinese walls were introduced in the commercial sector, basically for consultancy firms, such as in stock markets and so on, legal companies, various kind of entities like this, where basically you would have multiple clients, okay, and you would, however, have conflicts of interest between some of those clients. Perhaps they're rivals within the same sector. They're two oil companies or they're two banks. And but you still want to offer consultancy services across like a broad industry. So what you do is you create Chinese walls between the organizations, which were actually physical walls which you would put down in the workspace, so that people on one side of the wall would not talk to people on the other side of the wall about their consultancy matters, but yet you could still address all these clients. So this is the idea behind the Chinese wall. It's a very old concept, originating in the stock market, but it's also highly relevant for computer systems, you could imagine, because we have things like cloud computing, where you have servers with the same hardware with multiple organizations using the same hardware. We have like all sorts of cloud services where there's lots of sharing going on. And of course, we still have the classic use case. We still have bankers and other people exploiting their position in order to get an advantage for their own gain within the stock market, which remains like to be a serious problem, as we'll see here. So all you need to do is go to, for instance, the Financial Times, insider trading reel, and this was in 2024 when I published the first paper, which I'm going to introduce. And I just needed to look at a few. Well, this is May the 21st, May the 3rd, May the 2nd. This guy, he was convicted of insider trading. A Merrill Lynch banker's named in some kind of insider dealing case. Okay, this is March and April 2024. So you don't really need to dig very far to find all these things that are going on. What do we have here? British billionaire Joel Lewis avoids US prison in insider trading case. But what did he do? He had to run away to Argentina, by the way. My co-authors are from Argentina, so they know all about, he's basically a friend of their dodgy president. Apologies if anyone's Argentinian and loves this guy, but I doubt that very much indeed, because he's actually he's attacking academics at the moment, making it very difficult for them. Okay, Germany's very serious about everything, including insider trading, so the German guy here. What else do we have? Okay, so this is February. This is still 2024, within 3 months of each other, lots and lots of cases. Oh dear, January 12th, 2024. Morgan Stanley pay 249 million to settle some kind of trading case. Okay, so there's quite a lot of at stake going on if you do not manage your conflicts of interest well, if information flows to the wrong people. And of course, you can't stop the people who really want to get hold of information, because of course, if you log into a system, you can always take a screenshot of take a photo of the screen, maybe post that in the internet, which is kind of what happened in some of the Pentagon leaks recently. So the guy just went in, he took a picture of the screen, and he posted it on Discord, okay? You can't really stop that kind of behavior, but at least what you can do is if you stay within a particular system, a computer system, you can ensure that if you use the system, then you don't inadvertently get hold of information from two sources at the same time, which you shouldn't simultaneously have, and therefore be in a position where you potentially can be accused of having a conflict of interest. You don't want these kind of fines, do you? As an individual working in the organization, as the leader of the organization, you don't want this to happen. But also, there are situations, so you'll have seen conflicts of interest all the time, as PhD students, for instance, when you're submitting papers, and you have a conflict of interest. If someone is submitting a paper from your organization, from your university, and you're trying to review it, that's a conflict of interest. You should not see that information. You should not even be aware of any discussion that's happening in that process. Okay, so conflicts of interest are kind of everywhere, and they're serious, and also in the academic setting, even that there you could be accused of all sorts of ethical violations if you were to violate a conflict of interest. It's important for your integrity as well, even at your level, not just at this kind of level. So conflicts of interest are important. Okay, so here's an example of a security policy which we can use to manage conflicts of interest. So how are we going to read this diagram? So objects here, this is the data. This is a security policy terminology for data. So we have object 1, object 2, object 3. And we have the subject here. We have subject 1. Okay. And then we have the two conflict of interest classes. Okay. This conflict of interest class could be, like, for instance, between two oil companies. And that means that information cannot flow from here to here, nor from here to here. It cannot flow between the two oil companies. And here, this is another conflict of interest class, maybe banks, but there's only one bank in that class, okay? So, initially, when you have, when you're acting as a consultant, when you're a subject, you can read and write absolutely anywhere. There isn't a policy saying that you can only read this person's data set. You can actually read anywhere. So for instance, I could read and write to object 2. So this is for a particular oil company as a subject. Yes? I can perform read operations and write operations. So the arrows going both directions shows read and write capabilities. But then I could also read from object 3. Why can I read from object 3? Because there's no conflict of interest between object 3 and object 2, is there? Okay, I said there's a conflict of interest here, but not here. So I can read from both of these organizations. But notice here, when I read in a Chinese wall policy from object 3, I've lost the write capability. There's no ability to push from subject 1 information into object 2 anymore. I've lost that ability. So I can read now from subject 1. Well, subject 1 can read from object 2 and object 3. Perfectly fine to hold that information. But I cannot read and write anymore to object 2. I can only read from object 2 after this operation. So what can happen is, as you are reading more information, initially you have this complete freedom to do anything you like. And so the first operation, I could have done anything whatsoever. But the more and more that I look at, the more and more that I read, the more and more potential I have for conflicts of interest, the less and less operations I can perform. So I can read and read more and more, potentially. But as I do so, write access can be revoked as you're going on. So this is quite a novelty of Chinese wall policies, is that as you're going along, the more and more that you read, the more and more that you consume, the less and less that you can write. Okay? These are dynamic policies. There are not many examples of them in the literature, actually. Okay. What about this one situation here? So I'm in the situation where I have the subject who has freedom to read and write anywhere, and they've chosen to read and write here. Okay, so I can do this. Is it possible, though, as a subject, to just write information to object 2? Can I just push information? So I can just append information to some data set. So it is possible to write without reading. Okay, but if you go back to the definitions of the Chinese wall policy, and this is where the formal methods are starting to kick in, it's difficult to know whether that is true or not. Because the definitions, this is from 1989, are in this kind of form, which is kind of blah, 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 blah. There's some N's and V's, and there's this notion of access that is appearing here, and then suddenly, down here you have, like, for instance, you have the notion of writing. So write access appears, and then you have this notion of reading, but up here there was just talk about access. There wasn't a distinction between read access and write access. Yet it seems that in these policies, read and write access have very different behaviors. Yes? So this is not really acceptable as a definition, a formal definition on which you can base something as important, which is regularly triggering multi-million-dollar fines in the industry. You want to have more precise definitions than this. So what we've done, what we can do, is we can use our knowledge of formal methods to give more precise definitions of what we mean by read access and write access. So we give operational rules. I'm sure the majority of people here have seen operational semantics before. Yes, so you have a label transition system, so you have a state, which makes a transition to another state, and then there's some kind of operation that occurs. In this case, you're reading, well, the subject S is reading object O, okay, and making a transition to another state. And you can see here that after having performed the operation, N, which is basically an access matrix, has been updated so that that particular read access is recorded, okay? And then there's a condition up the top, which is the conditions under which you can perform this read access. And this particular condition is called the simple security rule. This is from Brewer and Nash. And the simple security rule says, this subject can read this object if, for all objects it has read previously, which are in the matrix, okay, either the data set of that object is the same as the one I'm trying to read from, or the conflict of interest class is different. So I can read from a different conflict of interest class with a different data set, or I'm in the same conflict of interest class as before, but it's the same data set. So if it's an oil company if I've read already from oil company 1, I can't read from oil company 2, but I can read still from oil company 1 again. Yes. Okay. Now for write access, what does the operation look like? So we have here a very similar condition. So write access is possible, and N is just a read matrix. N is just representing your read operations, by the way. So there's no write matrix in this particular definition. It's just saying the conditions under which it's still possible to write. Okay. And this rule is conditional on another property here, slightly different. This is called the star property. Okay, so the star property is saying what? If I have a subject and an object, which I've read before, okay, so this is the same subject, it's a different object potentially, then the data set must be the same that I'm writing to. Okay, so if I've written to one data set, then I can still write to it. So if I've read from a data set, then I can still write to it. Or the data set which I've read from previously is some special data set called the sanitized data set. Okay, so what is sanitized data? So sanitized data, it depends on the context of your system. It could be data that is public, it could be data that's been approved to flow through the system, maybe it's been declassified. There's all sorts of reasons why the data might be sanitized, but it's basically free for anyone to use. So I can read as much sanitized data as I like. That's basically what this is saying. And I can still write information based on that sanitized information. Okay? That's it. So operations are very simple. However, if you read the English text, which I showed you earlier, given the definitions, it's really ambiguous what they actually mean. So it could mean that they actually, if you look in the literature, possibly Brewer and Nash meant this. So what's happening here is when I write, the read operation has been updated as well. So when I write, I also get read access. But if you look at the work of Sandhu, who is another famous person in this area of security policy models, notice here, there is no update. This is interpretation of his policy model. There is no update to the read operation when I perform a write. So writing does not entail reading. But again, if you look at Sandhu, it's just English text. There's no formal definitions. Okay? So that leaves a lot of ambiguity, because it could be that that one person implements it like this. It could be one person implements a text like this. It could be one other person implements a text in another way. If you don't have a precise definition, there's potential for divergence between different implementations of Chinese walls policies in the system. You really do need to be a bit more precise in that, okay? Okay, so suppose we go for this operation where we can write without reading. What can we do? Well, one thing we can do is, well, because initially I haven't read anything, and the conditions on this are basically based on only what I've read before, because N is only the read matrix. There's no record of writing at all. It's just whether writing is possible. This is what this rule is checking. Then writing is possible anywhere, because basically this is vacuously holds initially. The precondition holds vacuously. There's nothing in N initially. I haven't read anything. So initially I can just write wherever I want. I can write from up to object 1, I could write to object 3, I could even write to object 2, even though there's a conflict of interest between object 1 and object 2. Now why is it possible then to write freely in this way, despite there being a conflict of interest between these two objects? Yes?
Because so you set out at the beginning the condition was information can't flow between objects in the same conflict of interest time.
Yeah.
And that's still not possible.
It's still not possible, because information is only flowing from the subject to the object, but not from the object to the subject and then back again. Precisely, yes. So there's a kind of implicitly there's a kind of confidentiality property, isn't there? Which has been retained, which is allowing this greater freedom. So in fact, this rule seems to be pretty safe, this more free rule by Sandhu. What else can I do? Oh, but still, if I eventually do choose to read from object 2, then the situation changes, doesn't it? I can now no longer write anywhere, so I lose all my write access. So write access gets revoked across the board as soon as I perform one read operation. Initially, I can have freedom to just read anywhere. Write anywhere. I just read one place, and I lose write access everywhere. Okay? So this is again an instance of something which is quite rare in the literature. These dynamic policies where your write access, your ability to influence the system or send information, is becoming more and more restricted as you proceed through the system. Okay? Here's another example. So if I just take those two rules, right? We've got a rule for read and we've got a rule for write. Then am I allowed to do these operations? So basically what's happening here? Firstly, I'm writing to object 2. Then I can still, even though in the previous example, as soon as I read from somewhere, I lost access everywhere. If the information is, however, sanitized, I can still read and I can still write. Yes? Because the sanitized information is basically safe to flow through the system. It's always possible to allow this kind of public information to flow anywhere in the system. So I'm allowed to do that read operation without losing access, like in the previous slide. I can then write over here still. without losing access to this read and without losing access to this write. Okay, I can still do that operation. I can then, what can I do? I can even read and write to the sanitized data set. So I can be writing over here and I can be writing over here, and I can still read and write to public data. I can influence the public data. Okay? And then even when I read over here to this data set, I don't necessarily need to revoke read access to the sanitized data. I can still have access to the sanitized data. So sanitized data has this very special status. It allows a lot more operations to take place. All these operations were allowed by the rules which I provided. If you're worried that at this point that I only gave a read matrix, even though the write access is really important here, it is possible to give a definition where you have an explicit write matrix as well. And inside that operation, so it's basically the effect is the same. This is sound complete. These two models are equivalent to each other. They're bisimilar to each other. So what happens here is when I am performing a write operation here, I am updating the read operation as well. So this is Brewer and Nash's interpretation where when I get write access, I also get read access. But because I'm updating the read operation, therefore I have to remove from the write matrix all of those things which are in different data sets from the place where the object is where I'm trying to read from. Okay? So you have to do this big operation where you're removing information from the write matrix if you want to make it explicit. This is again useful for implementations because probably for efficiency you do want to just do a quick lookup. Can I do this operation or not? And you just have a matrix for reading and writing. You look there, is it in my matrix? And it's only when you try and do something additional operation which you couldn't do previously where you need to change the matrix potentially that you consult these rules. So you have these matrices N and W at hand where you just look up and say, can I do my operation? And the fact that these are equivalent means that this implementation would also be correct. Okay? Okay, so a consequence of having a formal definition allows us to be more precise about what we mean by security in this context. Okay, so we can prove a number of formal theorems which are going to allow us to check whether we have come up with a decent definition which is going to actually satisfy conditions. So I've given a lot of chat, but it would be good to make these notions precise. And indeed, Brewer and Nash have a number of theorems, theorem 1, 2, 3, and 4 in their appendices, which they use as a criterion to decide whether a Chinese wall model is good or not. Okay. So theorem 1 is fairly straightforward. We can just give that definition. Okay. So basically it's saying everything in this matrix N, which we're accumulating as we're going along, is itself going to be satisfying the simple security rule as we go along. So everything inside the matrix that we accumulate, so if I take any two subjects and objects in the matrix, any subject and object in the matrix N, then whenever I take another object which is also in the matrix N, then the simple security rule holds with respect to this subject and object which I picked out originally. So everything as I go along is going to still satisfy the simple security rule. This is an invariant of the system. Okay? Whenever I perform an operation, I'm maintaining this invariant. Everything in my matrix N still satisfies simple security. Okay? And indeed, this is an invariant of the system which we defined. It's an invariant of the system. What is an invariant? It's basically something that if it holds in a state before the transition, then it will still hold after performing a transition. Okay? And the neat thing about this is you can code all this up in a tool called setlog, which is what my colleagues have been using from Argentina. So they're developing this tool. It's a Prolog implementation or extension of Prolog, which is allowing you to do set theory in a decidable way. So it just computes over decidable fragments of set theory. And basically, if you set up these transitions, these operations in setlog, and you set up this theorem and ask to prove it as an invariant of the operational rules, setlog will just automatically go through, crunch the rules, and say yes. So you're able to actually automatically verify this invariant inside setlog. Okay? It's a relatively simple theorem, but on the other hand, as I said at the beginning, it's a pretty important piece of machinery. There's a lot at stake behind getting these Chinese walls wrong. They need to be developed correctly, don't they? Okay, so we have automated verification of theorem 1 in setlog.
Can you ask a question?
Yes, absolutely.
What about if the object has multiple alias? So how you model that thing in this theorem?
So my hearing's not perfect.
So let's assume that particular object has multiple alias. So going back to your previous theorem, how we will model that thing?
Multiple what? Sorry?
Multiple alias.
Multiple aliases.
Let's suppose an object has multiple references.
Right.
Yeah. Let's suppose we have an object. It has reference ref1, ref2, ref3. So now in our policy, we are just talking about one reference. What about the other references? Might be they can create the conflict of interest.
Right. Let me think about that. So the question there, if I'm trying to understand it correctly, is that you could have an object which has multiple labels. It could appear in multiple data sets, because of the way it's linked to other things, perhaps in the system via pointers or whatever. It's possible to have this. In the Brewer-Nash original model, every object has a unique data set. Okay? But we'll look at generalizations of this model. It could be like something you could do creatively is you could allow an object to have a particular label. So we have we're going to cover this in more in detail later. But you can assign basically security labels to subjects and objects, and from those security labels you can determine where information can flow. And you could, for instance, have the intersection, use the intersection or union of labels, the meet and the join in lattices, in order to say that a particular object is in multiple places in the system. And then it gets, and actually the lattice-based security models will actually be able to handle that. So I think that basically you're looking for labels which are kind of like either the join or the meet of multiple data sets, depending on whether you're trying to read or write. So if you're trying to write to something to make it available across multiple data sets, you need to look at the meet because you're looking upwards. And if you're wanting to make something, you're wanting to be able to read from multiple locations, you're wanting to look down on multiple data sets from a particular point, you're looking at the join operation. But you can't do both. You have to choose between reading and writing in this kind of situation. So it's an interesting question. You could really be creative with lattice-based security in order to set up that scenario. Okay. So theorem 4. So we're coming back to this observation about the flow for a bit. Okay, so when you start in a particular object, remember when we were writing to two locations, it wasn't a problem because there was no information flowing from one object to the other via the subject. But if you're reading from one place and you're writing to another place, you're creating a flow. But then there could be another subject in the system who is then reading to this object, reading from this object, and then writing over here. And then you're creating an indirect flow right across from object 1 to object 3, okay? Brewer-Nash theorem 4 is trying to capture this. Essentially, they don't call it this, but basically it's a confidentiality property. And the theorem says either information is confined to its own data set. So if basically you have a flow of information, reading and writing, okay? If you have a flow of information, then if you start off in a particular object, you're going to end up in another object, and you're still going to be within the same data set. You're never going to leave the data set. So information does not leak outside of a company's data set, okay? So that's confidentiality property. Unless, of course, the data is sanitized. So if you took data from the sanitized data set, the public information, that information can flow into any data set. That's allowed. Okay, so how is this established? It's basically saying, if there's some kind of flow from object O to object O prime, starting in some state, then the data set of where you started off with is either the sanitized data, this is Y0, this is what Brewer-Nash called it, sanitized data, or the data sets are the same. So this is a bit like the star property, which we saw as a condition of one of the write operations, basically. It's very similar to the star property. But it's a little bit different because we have this funny symbol here. What does this funny symbol mean? I haven't defined it. And the funny thing here is, if you go back to this original paper in the 1980s, nor do Brewer and Nash define it. So they say information can flow, and then they state their theorem, but they just jump straight to their conclusion. And again, this is not satisfactory from a formal methods perspective. We have definitions. We need to have all definitions in order to be able to establish this. So we need to define what information flows. So firstly, we define information flow. Okay, that'd be a good start to actually define the theorem that we're trying to start with. And then we can use setlog again to prove that the star property is an invariant, much like we did for theorem 1. So theorem 1 was very simple, but we're using it an element of that very simple reasoning, using this automated tool setlog to just discharge the fact that the star property is an invariant. But this still doesn't quite say that the star property is invariant. It's asking for more than that. So what we do is we establish automatically in setlog that the star property is an invariant, and then we appeal to another tool, which is cock, and use that as an assumption, that the fact that the star property is an invariant, in order to prove the theorem with respect to information flow. Okay? This is our strategy. So we're doing a mix of, we're mixing between two tools. We've got one which is discharging a whole bunch of stuff automatically, and then there's a bit of inductive stuff basically, which you need to finish things off. And then so we jump into cock and we just do the very trivial inductive step inside cock, and the whole thing is automatically proven. Okay? As I said, like one of the cruxes here, the crux here is really, what do we mean by information flow here? Okay, so let's give some examples of information flow with respect to this definition, in order to kind of get intuition for it first. So can we show that information can flow from object 2 to object 4? Okay, let's see. So we have object 2 here and object 4 here. What's happening initially is we have read access. Subject 1 has read access here and write access here. So you can see information can flow here. It can even get as far as subject 2, because subject 2 could read from object 3, couldn't it? That's quite reasonable. Yes, as a starting point. You can imagine we've gotten as far to get that far. Then what we could do is subject 1 could read over here. So it can read from object 1. Okay? Now, what happens when I read from object 1? Well, you know from the very first slide that I have now read too much. I've read from a different data set, and therefore write access here is revoked, and subject 1 can only read from these places now. There's no conflict of interest, so I can read everywhere, but I cannot write between the different data sets, okay? So I've lost write access, so it looks a bit like this flow here is broken. But of course, you have to take time into account, okay? There was a time in the past where information could flow from object 2 all the way to subject 2, yes? So it needs to be based, information flow needs to be based on traces, yes? You need to consider basically read and write operations along a trace to take into account the time, because this write operation here is going to create the flow from object 2 to object 4, isn't it? Even though there's no direct flow anymore set up. At that particular moment, if subject 1 tried to read from object 2 and then write to object 3, we'd not be allowed to do that. But in the past already, S2 was able to receive the information, which has flowed all the way from object 2. So we have an indirect flow, okay? So we need a good definition of information flow, which is going to capture this kind of flow. So formally, like in the operation rules, you can build up these write operations and check that they're all conformant with the rules that are provided previously. So you start off with the empty state, the read matrix has been updated, the read matrix has been updated, etc. as we go along performing operations. Okay, so this is within our model. It's allowed as a flow from object 2 to object 4. Notice still within the same data set, so it doesn't violate the theorem. So how can we define this? Well, we need maybe some definitions. Let's define big steps. If you can perform some operation, then I can do a big step. So doing one step is already a big step. And if I can do another operation and then another big step with where I can read or write here, so alpha is either label, then I can do the big steps. So I can do an arbitrary number of random operations before performing the operation which I'm interested in. Okay, and that's allowing kind of strange things happening, like for instance, this operation was not part of the flow, but it's still part of a trace. Yes, we're allowed to skip these things. That's why we have the big step semantics here. And then we can define information flow. So information can always flow to itself. If an object has the data, it has the data. Okay, so there's a trivial flow to itself. And then, if I want to flow from object 1 to object 2, and there's another world, so these are worlds by the way, where I can, so being a little bit more abstract to encompass the multiple ways in which you could represent the state of the system. If I can perform a read operation as a subject, so I can read to object 2, and then I can write to object 3, and there is a flow from object 1 to object 3, okay, is this incorrect? No, there's a flow from object 1 to object 2, sorry, it's a flow from object 1 to object 2 inductively, then there's a read operation from object 2, and then there's a write operation to object 3, then I've created a flow from object 1 to object 3. Do you agree with that? Yes. Okay. So we have a definition now. So we've already improved over what Brewer and Nash wrote originally. We were able to actually define information flow, and therefore we can establish the theorem. And of course, this is where COP comes in, is it needs to deal with these inductive definitions. So just iteratively, it goes over, unfolds this definition and checks that the star property is going through it all. Well, that's done as an invariant, and then uses that fact to establish the theorem, which is theorem 4, which is the confidentiality result. Okay? So we've already gone beyond Brewer-Nash in a few ways. What have we done? Firstly, the definition itself of the operational rules were not clear. They were ambiguous. So we've made them more precise. We've given them precise definitions. And therefore, your implementation is more likely to be correct if you follow that definition, because it's really clear what we mean by making a read transition or write transition. Okay? What else have we done? we've looked at the theorems, and we found that the theorems were not even well specified. And we've clarified the definitions which are required in order to just state the theorems. Okay. Contribution number 3. We have not just proven those theorems, but we have done so in such a way which they are mechanized, so they're checked by proof assistants. So we got this additional layer of trust, of assurance, which is going on by using formal methods. So formal methods has helped us in a couple of ways here. It's helped us be really precise so that systems which implement Chinese wall policies can be more accurate and actually a little bit more general, because we've shown that the slightly more general interpretation where you can write anywhere initially is actually perfectly fine with respect to the definitions. And then we also have this additional trust that that more general definition is in fact good, because we have proofs that confidentiality is still maintained. Okay. I gave theorem 1, I gave theorem 4. So you can imagine there's a theorem 2 and a 3. Theorem 2 is rather trivial, and maybe a little bit underspecified. Maybe, if we have time, we can talk about why. It's not obvious why. There's also theorem 3, which is a little bit more non-trivial to prove, which has also been discharged in set log. But I don't want to talk about that. There's a good reason why I don't want to talk about that, because I claimed at the beginning I was going to do something you absolutely shouldn't do, which is to present new material, which is under development up to now. You can find all this in the paper, by the way. But I want to actually get to the new material. So let's recap where we are just now. We have the operational semantics, we have a clarification of information flow, and we have set log discharging most of the proofs automatically, and a teeny bit of COC just finishing off one of the proofs for the inductive definitions. Okay. So I started in 1989, so you expect me to go forwards in time if I'm going to present new stuff? No, I'm going to go backwards. So in 1989, you go to this paper by Brewer and Nash. It's one of the most cited papers in information security, like has the highest impact for that year in terms of number of citations, normalized. It's a really influential paper, and yet it still has all these problems. Okay, so if I go back further, what I find is the inspiration for the Brewer-Nash model, which is the Bell-LaPadula model. Has anyone come across this, by the way? Bell-LaPadula, yes. Usually if you do an information security course, it will pop up somewhere. Okay, it's the classic information flow security policy model example. And basically it was developed by the military. So you have top secret, you have declassified, and you have classified in some sense. You have a hierarchy of different policies. Okay, so that's why the representation is now changing a little bit. We're drawing a kind of a lattice, an ordering over data sets instead of having this flat structure that we saw before. Okay, and you have there a star property and a simple security rule, which you've seen already. Okay, but in this lattice-based scenario, basically the simple security rule is saying that subjects can read down to objects. Okay, so what's that? So suppose I'm subject 2, so I can read down, I can read to object 1, so that's shown here by the information flowing from object 1 to subject 2. Of course, information can flow from object 4 to subject 2, and object 2 to subject 2. Okay, so I can see everything down below me in my lattice. So if I'm an agent who has this level of classification, I can see all this information, including the things of lower classification. But I can disclose information to my boss. I can say, well, I found something interesting. I'm going to put this as top secret information, so I can write upwards. Yes? Okay? And that's captured by the star property, which is basically subjects can write up. Okay. So the star property and simple security rule we've seen before, but this is a slightly different incarnation of them. And what I could do, for instance, here are some rules that I can perform. So I have, in this case, I just have top and bottom, high security, low security, a bunch of subjects, a bunch of objects. So subject 2 is reading from object 2. Subject 2 is then writing to object 4, yes. Then it's subject 1 is reading from object 4. And then what happens is subject 1 can then write to object 3. And I've added a couple of annotations here. Copy and erase, these are not really part of the operational rules, but it's suggesting something that could be happening here. Is it could be that this write operation was creating a copy of object of the information is just read from object 4. So it's created a copy up here. And so effectively what's happened is if you've copied information from object 4 and then written it up here, what you've done is you've declassified, you've reclassified upwards object 4, and it's become of the classification of object 3. The classification has gone up. So it seems reasonable that objects can be made more secure as the system goes forwards, yes? Would you agree with that? Yeah? So I can classify up. But notice something else here, look. Object 2 was read from before that reclassification upwards happened. So information from object 2 has tarnished information in object 4. Yes? Okay? It's entirely possible. Now bear that in mind, I'm going to come back to this point. So I've reclassified object 4 upwards to make it with just legitimate read and write operations allowed by the simple security and star property. So I could define this. If I go to Bell-LaPadula's model, then they have a special case where what they're doing is they're trying to, sorry, there should be a slide here. Never mind. So they have, basically, if you interpret their rules, you have read operations and write operations here. So what's happening here is I have a transition from one world to the next. Okay. I think this slide is quite important. I wonder why that's happening. This is a bit busy. No? Okay. Never mind. We'll just go for the busy slide. Okay, you can consume this information. So we have an object which has been read, and of course by the simple security rule, the label of the, so what this is doing is assigning basically a label to each of in each world there's a assignment from subjects to labels and objects to labels. Okay? Whether it's low, high, etc. Okay? And the subject must have a higher classification than the object in order for the read operation to take place. Okay, that's the first bit here. And the other two conditions are saying what? Okay, when I move from this world here to this world here, then what's happening here to the subjects? The subjects are allowed to go up. So the subjects are allowed to float up through the system. So basically you can become promoted in the system. Okay, so if you think about the Brewer-Nash model, initially you could read and write to public, and then you get promoted so that you can read and write to a particular data set, okay, as you're moving forwards. So that's allowing the subjects to float up. But according to Bell-LaPadula's declassification model, objects can be declassified as you move forwards, okay? So look, the object here, in the initial state is higher than the classification of the object in the other state. And that feels like the opposite of what I've just said. Remember what was happening. I was starting off in a low level. I was taking an object from here, object 4, And I was effectively copying it upwards. So it was being classified up, not downwards. Yes? And surely that's a violation of information flow. This is 1973. This is probably the most famous security policy model. If I go through it, what happens? I can read from object 2. I can then write to object 4. I can then, what's happening here, I can declassify object 4, so it goes down a class, yes? So object 4 is actually moved this time. It's moved a bucket down. And then subject 3, which was at a low classification level, is able to read information from object 4. And look, that includes not just information from object 4, but also information from object 2. So there could be highly classified information which is flowed to object 4, and then has been declassified along with other information in object 4, and then is available to lower class subjects. That's not good. Okay, so basically you're leaking information if you follow this property. But something that's really fascinating about this, because remember I was scrutinizing the definitions, the theorems, the criterion which Brewer and Nash gave. The same applies here. If you take the criterion of Bell and LaPadula, if you take their theorems, according to their theorems, this is a secure model. So obviously their criterion are not quite adequate in order to judge security. You would agree. And this is not a new thing. I'm not the first person standing up and saying this. If you look in the past, there are some famous people who've also criticised Bell and LaPadula. Okay? When you criticise Bell and LaPadula, you have to be a little bit more succinct than that, or a little bit more careful. There are many models actually defined within a volume of 3 papers. Okay, so this is one particular model that I'm picking up on. But it does show that given that their definitions of security actually hold for this model, there is a problem with their criterion for what it means for a security policy model to be good. Okay? Again, we have a role here. If we have formal methods, we can be more precise. We can find the criterion, which a better criterion for judging security. So, this allowed, notice what's happening here is an object has been declassified. That seems to create an information flow, but is it okay for objects to be promoted instead? I would say yes, because look, remember back, the first example that I gave of the Bell-LaPadula model, we were reading from below, and then we were writing upwards. We were just copying things upwards. And that was perfectly fine. That was actually didn't actually involve any movement of objects. It was simulating the effect of an object being reclassified upwards. It should be okay to allow an object to be reclassified as top secret, which was public. Okay? That should be allowed. So we're allowing objects to move in the system, creating dynamics for objects as well, not just subjects. Okay? Really dynamic policies. So let's develop that model. Never seen before. Live on the board. Here we go. Who's going to start? But I think it's possible in the last, so I have about 20 minutes, yes, the last 20 minutes to develop a very general model which is going to fulfill the criterion of Bell-LaPadula with the reclassification of subjects upwards. So subjects can be promoted, objects can be classified upwards, sent up to the reclassified at a higher level, and also general enough so that we also encompass the Brewer-Nash model at the same time. Okay? So how can we do that? Okay. So, firstly, we need to be more precise about our definitions again. This is a formal method school. And so I think all of you will have no problem of deciding that this pre-order is reflexive and transitive. You know what this means, okay? So you have a reflexive transitive operation. That's all we're assuming about the operation. And we're going to define, so we've got worlds. Remember, worlds are now mappings from subjects and objects to labels, security labels, okay? And the worlds are ordered if point-wise, for every object, the label only goes up. Okay, so that's allowing the objects to go up and the subjects to go up. Okay. Star property. What we can do is we can simply allow writing. So the subject can write to an object if the object is above the subject in terms of classification. So I can disclose to my boss, and I can disclose to people at the same level as me, but I can't write information downwards because I might create leakage. Okay? Very simple rule. It's even simpler in the rule now. We're more general, but the rules are simpler, in fact. And the read operation is pretty much the same, except we're allowing this kind of level creep, it's called in the literature. The levels of the security levels of subjects and objects can creep upwards. Not only can we read information below our classification level as a subject. We had a couple of lemmas. We defined these big step operations before. If you have a big step operation, then basically you have a bunch of stuff and then a read operation. Then whenever you have such a big step operation, then level creep is always going upwards continually. These are trivial lemmas, you have to agree. And then the conditions of the read operation still hold. That is, the subject's level has to dominate the object's level. Okay? Same with writing. We have this lemma. And then from these two lemmas, we can then establish confidentiality as a theorem in very general terms. And this theorem says, if there is an information flow, exactly as we defined before, so we've defined information flow in the previous part of the talk. So we have these zigzags, read and write operations, yes? If we have a flow from one object to another object, then the level of the object in this initial state is going to be below the level of the object in the state afterwards. Of course, in the meantime, the object could have gone flying up to the first object here could have been declassified way up. It is at the point where you initially read where the flow is stemming from that's important, the level of the object at that particular point. And that's why this you need this kind of information flow definition to be traces to take into account time, okay, the time of particular operations occurring. And this just comes out relatively easily. We could prove it in the board, but I want to kind of move on. You can probably do this in 5 minutes, I reckon most of you. Okay, so how can we, so I said we could do Brewer and Nash, and we can also do Bell-Padula at the same time, the same model. What do we do? So what we do is we take this lattice model, which where you have this P order, inspired by Bell-Padula, and you add a join operation. And this is a contribution due to someone called Sandhu, who's a key person in the area of information flow policies. And you allow a special label to exist for any two labels. So if I take any two labels, there will be another label which is the join of the two labels. Okay? So that join operation is going to be above these two labels, isn't it? And what does that mean according to the simple security rule? Remember, I can read downwards. It means I can see both of the labels. I can basically read information from both data sets, yes? But can I write? No, because information can only flow up. So if someone else was just inside one of the data sets at a particular level, they could probably send information to me if I was up there. But that's effectively the jewel of writing, of reading downwards, isn't it? Yeah, so I can read, but I can't write. Information can't flow up. Okay? So if we create these join operations, then I get these positions inside these security labels, special security labels that I can float up to as a subject, where I can do the operations you saw in the first part of the talk, where I can read information from different data sets, which are in different conflicts of interest classes, yes? But then at the same time, I lose access, write access to everywhere. So I'm no longer able to write. Remember, write was being revoked. That was a key feature of the first model. Okay, so write access is no longer possible across the board. Okay, so basically all I do is I create these join operations. These exist whenever like usual conditions for joins hold. I'm pretty sure most people have seen this. Okay, it's like an OR operation. And boundless completeness is the only condition I need that says if you have two labels which are bounded above, then there exists a join. Okay. So I don't need the full power of a lattice here. This is more general than a lattice. So I mentioned lattice-based security policy models earlier. That is the tradition. In fact, you don't need the full power of a lattice in order to be able to get these policy models working. You just need this condition. So I have what you see before plus joins. So I can do the following operations. We have a subject now. We have two objects, two different data sets as before. I can write up here as allowed because I'm below. I can write up. I can then read over here. That's allowed. The subject is allowed to read from O3, but the subject floats up in the process. Okay, because can it read here? No. I can only read downwards. I'm too low to read, so I need to float up to O3, to the same level as O3, in order to be able to read from here. And in the process, of course, I've lost my right access. Oh, that's my very first slide. Okay? Yes? The very first slide right at the beginning, the Brewer-Nash model. Okay? Implemented using lattice spaces, in a lattice-based approach. What can I do now? I can read and write here. I can also perform a write operation. And furthermore, I can also read now from object 2, but when I do that read operation, I have to float up to this special label, which is the join of the labels of these two data sets. Okay? And from there I can still read from object 3, and I can still read from object 2. Again, this is just a recreation of something that you've seen previously earlier in the talk. Okay? So the Brewer-Nash models can be cast in terms of lattice-based models by making use of these join operations. Okay? Where you can see multiple places. Okay. So how are we going to formalize this? Well, we need one other condition. So we have the rules as before. The simple security rule is not changing at all. Basically, I can, as a subject, I can read everything below me. Condition is still the same. But whenever I make a transition, I make sure that the subjects are bounded. And what does bounded mean? It means every subject has not yet reached the top level of the matrix. Okay, so matrix of the lattice lake structure. It's not a lattice. It's a bounded complete full set of that. Okay. So you have not reached the top. Basically, you haven't reached a point where you are in a position, so it's not so obvious from here. For these two labels, there was no conflict of interest, so I could basically find such a join. If there was a conflict of interest with another label, label 3, with another object, then if I tried to take the join, either it would not exist or it would be the very top element of the matrix, of the lattice. Okay? So basically what I'm saying is subjects cannot reach that level where they get to the very top and you can see everything. Okay? So subjects have this restriction. You're not allowed to reach the top level. Okay? But you can reach all these intermediate points. Okay? And then what we can do is we can define something, a theorem, which is a notion of what does it mean for there to be a conflict of interest in the system. If you have a world which is bounded, and I perform a read as a subject from object 1, and then I read from another object 2, then the join between the labels of these two objects from which I've read, object 1 and object 2, in the relevant worlds, okay, it's got to be strictly less than top. Okay? Top, remember, is what happens when you join two things together and they're in conflict and you just bump right up to the top of the lattice structure, okay? Okay? If you've done that, then you have a problem. But if these definitions are good, if there is no conflict of interest, then any two objects that I read from as the same subject are going to be such that when I do try and join them, there is going to be a nice point there's a vantage point inside the structure of labels where I can sit and I can actually genuinely see these two objects without a conflict of interest. Okay? So this is the conflict of security. Attempt number 1. To keep things really on the edge, and so I added another slide 30 minutes before starting. Say, well, actually, that definition is not good enough. It's not really obvious why it's not good enough. Can anyone see any limitations here? Think about information flow. So remember here, this is saying like I can do a big number of steps, and then I can do a read operation, and then I can do a whole bunch of other steps, and then I can do another read operation, both with the same subject. Can anyone see something that's missing here? Statement. It's not obvious. Okay. Where do you see clearly? Suppose I have a subject like this. Okay. And they are trying to read from multiple objects. So we've got object 1, object 2, object 3. Okay. And there's a conflict of interest here. So we have a conflict of interest here. Okay? But you had a security policy model which allowed the subject to read from here and write from right to here. Okay? So information can flow from this object to the subject. So there's an indirect flow. Okay? You could have another subject, subject 2, which can then read from these two pieces of information. Now, notice object 2 and object 3 are not in conflict. There's no conflict of interest between object 2 and object 3. Yes, you see that? So if I just look at the label at the point of reading, there's no conflict between these two labels, and so subject 2 has no conflict of interest. But there's an indirect conflict of interest because subject 1 has taken information and has written it over here to object 2. Okay? And now there's information coming from object 1 and object 3 that S2 holds, and S2 has an indirect conflict of interest. Okay. The reason why I added this recently is because we were trying to decide whether like some other security policy models were good and bad, and there was clearly a problem like this. And yet all the theorems which you've seen previously hold for those security policy models which are clearly broken in a sense. Okay? So sometimes you need to actually come up with new theorems to strengthen the other ones, to come up with a stronger criteria to determine whether a security policy model is good, whether security property holds. This is really typical in security. You're doing this all at scale all the time. So attempt number 2 is what we can do is we have to basically refer to traces. And we have a notion of whether a trace satisfies a flow, and it's basically the same as before. We have these zigzags, but with respect to a specific trace, not an arbitrary trace. And the reason why we want to do that is because we want to talk about one trace, and with respect to that one trace, we have a flow from object 1 to a subject, and then we have a flow from object 2 to a subject. So we've got the flow from object 1 to the subject, and the flow, fungible operations to the same subject. Then those two objects should not be in conflict at the point where they were read initially. Okay? So we build the flow into the conflict security definition. Okay? We needed that in order to pick up on this kind of scenario. Okay. Where are we? So we have this generalization now of Brewer-Nash models. We have, which also encompasses Bell-LaPadula, but with this novel feature, we've not seen before, where objects and subjects can both float up through the system. Okay? We also have a stronger criterion than previously for determining whether a policy is good. So we have the previous clarifications you've seen, 1, 2, 3, 4 clarified, information flow clarified, but we also have a further, even stronger characterization of whether a Chinese wall policy is actually a good policy. Okay, this enhanced conflict security. But what's nice about this is we can basically reverse all the definitions, and we can get back the original theorems. Like in this very abstract model, very general abstract model, we can basically prove everything in an easier way than before, and then we can cast everything back to the original definitions. Okay, so we can also show that all the theorems that we hold with respect to the original concrete model or specific model that we had originally in the system. So, but all you do is you basically say you have a notion of Brewer-Nash conflict. They're in conflict if they are in the same conflict of interest class with different data sets. Okay, we know that definition. Lynn had a more general notion of conflict. He noticed that was not general enough. And so basically he defines a symmetric conflict of interest relation. There's a relation like this between two things whenever there's a conflict of interest. There are things you can express which you can't in the original Brewer-Nash model. And you can then define what it means for the joint to exist, okay, and check that it satisfies all the properties that we had previously. It's reflexive, transitive, and complete. Remember those definitions we exposed? If you show that these models actually satisfy these abstract definitions, then you know that the theorems are going to translate back into the original model. Okay? So you can do this trick where you can sometimes raise abstraction and generality, and actually things become simpler. And then you can cast them down and say, well, actually, I program them up here, and these properties still hold for the whole range of ways you could instantiate the models in a particular more concrete way, which is perhaps closer to what is used in a particular system. Yes?
So this is kind of like a refinement.
You could see it as a kind of refinement, yes, or a concretization, or that's a good question. What do you call that process? Instantiation?
So
You
start with the other.
It's kind of like a refinement process, isn't it? Yeah, you've got one is a refinement of the other. You've got the very, very abstract model, and you've got these refinements, which are all satisfying still the properties that hold for that.
It's almost like reverse engineered in some sense. Taking the abstract from
Yes, in formal VeTSS terminology, probably refinement is correct. Exactly. So are we fully general? Not quite, but we're also out of time, I think. So let me just give a cap of the final slides rather than go through the details. Basically, we had subjects and objects, but what Sandu wanted to do is he wanted to separate subjects into subjects and users. Now, why do you have that? Because a user can have multiple subjects that can flow through the system on their behalf. So that's basically like when you're opening multiple tabs in a browser or different windows or whatever, they might be doing different tasks. And as long as information is not flowing between the different tabs, like they're isolated from each other, maybe you can get the one, if you stay within, keep each task within each tab, you don't copy information from one and paste it to another, then maybe you can still do more things because you can start further down the lattice and float up. You don't. It's not the case that once a user's logged into a system and they've read a certain amount of information, they can never get that back down again. They can't. They float up. It's going to limit the subjects that they can create in a particular way. But subjects can start at the bottom and they can do more operations as long as they don't interact with each other. Okay? Basically, that's what's happening here is basically you can see the model is pretty much the same, except for there is this mapping from users. Basically, every subject has a user that they're associated with, and every subject is bounded by the level of the user. So the user will still never have any two subjects which are going to create a conflict of interest, even if the subjects can be in different parts of the lattice below the user's level. Okay? You can see that this is just, basically, this is it. If you want to capture Sandu's model where he has users, you just modify the system just in this tiny, tiny way, and everything falls through, and you get this conflict of security again. Okay? So, once you're at this level of abstraction, it's quite easy to kind of add features as well, it seems. Okay. So we have what Sandu intended. Users can float up, but not to sys high. Sys high is the top where there's a conflict and you can see everything. Users can create subjects at lower levels. Users can read using subjects but cannot write, otherwise information can flow from one tab to another. Objects can have any label, so subjects can't go up to the top, but objects can. Now, why is that useful? Because you might want to have system logs where you're kind of logging information which can be seen only by some administrator who's sitting at the top level, yes? Who's different from the user, it's a special kind of user, okay? So you have some kind of auditing service, okay? You can push information from processes right to this auditing level where it can be seen. It can be written there, but it can't be read by any user of the system. We have joins allowing us to do Brewer-Nash stuff. We have some further generalizations. We're going actually beyond what Sandu and Brewer-Nash intended, somewhat. So we have this very general model. So it comes to Sandu, Brewer-Nash. Then I mentioned very briefly this kind of like very general kind of conflict of interest relation. Bell-Padula, EBA is basically Bell-Padula upside down. When you're talking about confidentiality, it's due to integrity. EBA is talking about integrity. Okay, it's like from where you've written the information, where did that information you're reading come from? Rather than where is this information that I was writing, where does it go? It's just like we can do this kind of refinement, this concretization. If you can show that an existing security policy model satisfies these few definitions which we've distilled, then you know that all these properties come for free. Yes? And it might be in these models that there are additional information flows which are perfectly legitimate, which are not allowed by the model, particularly in these more concrete models, but then that's fine, it can happen. But it could also be the case that if I try and do an operation that is not allowed by this model, it might be that there's a practical reason why you shouldn't be allowing it. It might be that there is a reason why you want to declassify something. It might be a reason why I want to hand this information from one company to another for a particular purpose. But when you have that violation here, then you know that you have to trigger additional mechanisms, like you have to ask your manager, or you have to log a system in some kind of legal way, which is going to allow the transfer of data from one organization to the other under GDPR or whatever legal constraints you have. Okay, so you know when there's an information flow violation. It doesn't necessarily mean it's absolutely forbidden. It might be in a real system that what you do is you just trigger an exception, a separate process for allowing information to be transferred elsewhere. So it's not as restrictive as it seems. It's very useful for ensuring that for operations that do stay within this model, you're not going to be fined 350 million as a company for information ending up in someone's hands where they should not have that information, and as a result they end up in court being accused of insider trading or something like this. You're at least as a manager of that system, if your users are going to be using it correctly, if you can prove that they're using it correctly, you know that such claims are not going to be brought against you. Okay? Yes? So you know the operations which are safe. Okay? So, I think I had an hour and a half.
And we've got 3 minutes left. So
Yes.
let's give Ross a round of applause. Are you taking questions?
Yes.
Are you? Okay, fire away. Have you got any questions? I'm going to ask one. Can you eliminate conflicts of interest by doing mergers between companies? Like, can you make your object kind of sets come together and then somehow eliminate conflicts of interest in the graph? Or is that something that happens out of the scope of these traces?
No, okay, so you could, so we talked about joins.
Oh, right, okay.
Yes. Okay, we didn't talk about meets.
Right.
So what does a meet between two companies? So it's lower bound. So it's something which you can, if you're at that level as a subject, where you're at the, okay, so you're at the, listen, you can see it right over here, but it's a very simple diagram. So you have label 0 and label 1. Their meat is going to be down here. So we have, okay, so suppose this is the merger of the two companies. Then if I put reports here, which are valid for this new merged company, what can happen to that information? So I could potentially still write information from the merged company to the old company, couldn't I? And if I'm inside the old company, I can see information from the new company, but not vice versa, okay? So is it in fact what we want for the merger? Do we want it to be a joint operation? So actually we could put the objects up here. Maybe this makes more sense for the merger. Because information which was created from the old company, L1, and the old company, L2, can still flow to that new company which you created, but not back into the old company. The old company is somehow ring-fenced, yes? So perhaps, in fact, so I do the wrong operator here, the join operation should be for the merging of a company, okay? But if you were to have a company that was to split into two entities, probably you would consider that operation, that old company, which was split into two parts, to have been the meat of the two entities which you previously used. Thinking about whether, like, the company is splitting or whether it's coming together might affect where you actually label it in the system. So it's an interesting question. You can be really creative with meets and joins, depending on, there are other features of these policy models which you can be creative with in order to express things. Yeah.
So, right near the beginning, when you introduced Bell LaPadula, you talked about declassification and how that's actually not safe and it can cause all these problems. So I'm guessing that would fit in here as one of those kind of exceptional procedures you have to go around the outside for. Is that correct?
Yes, exactly. That's the kind of exceptional procedure. So if you wanted to do a declassification, what would you need to do?
Well, so I suppose you'd have to make sure that no other information at that same level has gotten into the object you want to declassify.
Right, and then what do you need to record for that?
All the rights to the object.
Basically, you need to record all the information flows, don't you?
Yes.
All of the read and write operations across the whole system. So while declassification is possible, the amount of information you need to record in order to do that safe declassification is either it's huge or it's really disruptive. Basically, once you declassify one thing, you have to say, well, all of this stuff potentially could have been touched at the same level, and you have to just basically treat it all as broken. So the whole label just collapses. So this is why declassification is expensive, potentially. But it might be a smart way. You can just record the really important operations or something. So this is why it's more of a practical question. It depends on the context how you're going to handle declassification. Yeah, it's a good example.